Okay, now let's work some example problems for rotational motion. Here are the example problems we're going to be working. Pause the video and work these out yourself in advance so that you learn how to do it on your own. And there we go. All right, our first problem says describe the motion of object A and B, and then it says sketch the rotational velocity and acceleration graphs for these two. So first thing to notice is always read the axis. So this is angular displacement, so that's theta. This one is the same. All right, so this is a position time graph, an angular position time graph, or rotational position time graph. So first thing to note is remember that the slope of this graph equals the velocity. So we have a positive constant omega for this one. And since the slope is constant, alpha equals 0. So there's no acceleration. All right, so let's go ahead and sketch our graphs for this. So omega versus time would be positive and constant. And our angular velocity versus time would be really boring. It would just be 0. This one, on the other hand, is a little more exciting. We have a curve in our graph, and the slope of this graph equals rotational velocity. So we start with a rotational velocity of 0, and then we end with a rotational velocity that's positive and constant. So we must be accelerating. Let's assume that that acceleration is constant. The object is sitting still, and then it starts to speed up rotationally as it starts to spin. So what we start with then would be something that looks like this, and this would be a positive constant. I'm assuming it's positive and constant anyway. Well, we can tell it's positive. We just don't know from the graph if it's constant for sure. If it's a parabola, then it's constant. So alpha here, and so there we go, positive constant alpha. Oops, there we go. Easy. Problem 3 and 4 are very similar to our last one, except this time it wants us to describe the motion of an omega t graph. So that's our angular or rotational velocity versus time. So it's going to be a little bit different. So this one starts with an initial angular velocity. And then remember, the slope of this graph gives us acceleration. So we have a negative constant angular or rotational acceleration. And we end down here with a final velocity of 0. Okay? So it asks us to graph the position and acceleration versus time. So let's start with our position time graph, theta versus t. We are starting with a velocity. So assuming we start down here at theta equals 0, at an initial position of 0, we start with a slope of omega naught. And then we end at this time over here with no slope because our final velocity is 0. So that means we're going to have a downward pointing parabola, which makes sense because anytime we have a negative acceleration, we have a downward parabola. And then our acceleration versus time is much easier. It's just a negative constant, like we said before. So there we go. There's our negative constant velocity down here. And that was it. Problem 5 asks us to analyze an angular position versus time graph. So again, this is a theta graph. Asks us to find the rotational velocity and acceleration. All right, well, the slope of this graph would be the rotational velocity. So I've got a nice spot here and here. So it has a rise of 2/1. So we have an omega of 2 rads per second. The slope is constant, so the alpha is 0. And then it asks us to fill out the kinematics data for at 5 seconds from this graph. So theta naught, theta, omega naught, omega, alpha, and t. We know we're at 5 seconds. So we're looking for the information right here at 5 seconds. Well, we know the acceleration is 0. We know that our rotational velocity is constant at 2 rads per second. So these are the same. We begin at 0 position and we end at a position of 10 rads of angular or rotational displacement. In question 6, we're looking at an omega time graph. So this is a rotational velocity graph versus time. says to calculate the rotational displacement and the rotational acceleration. Well, let's do acceleration first because that's a slope and that's easier for most people. So our slope will be from here to here. I have two easy points. That's a rise of 246 over a run of 4. So that means alpha would equal a positive 1.5 rads per second squared because that's our slope. Finding the rotational displacement is a little harder. We need to find the area bounded from 0 to 5. So we have a shape that has a triangle here that has an area of, let's see, that would be 12. And this area here is a rectangle, so that's a little easier, 4 by 2, that's 8. And so we have a total area for theta of 20 rads. Now, our last thing is to create a kinematics table again. So theta naught, theta, omega naught, omega, alpha, and t. Well, again, it gives us the time of 4 seconds. We know the angular acceleration is a positive 1.5 rads per second. We know our initial velocity is 2 rads per second, and our final up here is 8 rads per second. Now, they didn't give us the initial position, so I'm just going to assume it to be 0 like we always do if they don't tell us. And so our displacement then was 20 rads from the beginning. There we go. Question 7 wants us to find the rotational acceleration versus time graph for this object and to also sketch the position versus time graph for this object, assuming we start at a position of 0. So let's do the acceleration one first. I'm going to draw mine right here and line up my times. So that's alpha versus t, that's 5, 10, and 15 seconds. Here's 0. So we start with a slope over here of 10 over 5, so that would be 2. And then we have a slope of 0, so alpha equals 0 here. And then we have a steeper slope here. Now they didn't tell us what this is exactly. That looks to be about 13. So that's a rise of negative 10 over 3. So that would be negative 3.3. And that would give us a larger negative acceleration down here than we had positive up there. Okay. Remember on the AP test, don't worry about these vertical lines. We know they don't really exist, but they help us line everything up. So it's okay to draw them. And then our displacement versus time, 5, 10, 15 again, 5, 10, 15. So we have a constant positive acceleration here and a constant negative acceleration here. So we're going to have an upward facing parabola here. And then we have constant velocity here. So that's going to be linear from there to there. And then we have a downward facing parabola with a final velocity of 0. So therefore it should top out here like this with that slope equaling 0. So we have a negative acceleration, positive acceleration, and acceleration of 0. So parabolic up, linear, and parabolic down with a top slope of 0. Question 8 says we have a string that is wrapped around a solid stationary disk with a radius r and a rotational inertia of 1/2 mr squared. The string is pulled with a force as shown in the figure. Let's assume the force is constant since it doesn't tell us. The disk is free to rotate about its vertical axis with negligible friction. So you got a disk with a string that's going to pull it and it's going to start speeding up. Okay? Now, I'm going to assume that this direction is positive since they don't tell us. And it says to sketch the rotational position, velocity, and acceleration. Now, we have a radius here and a force perpendicular to it. So this is going to produce a torque that's constant. And remember that the sum of the torques equals I alpha. So if the torque is constant, then the acceleration is constant. So that makes this easy. All we have to do is sketch our graph for constant acceleration. Theta, omega, alpha. Constant acceleration, constant acceleration, constant acceleration. And we're done. Remember that that is positive alpha here. Part B says use Newton's rotational laws of physics to derive an expression for the angular acceleration of the disk. So we're moving a little bit past kinematics, but that's okay. So it says the sum of the torques equals I alpha. That's Newton's law. It's the rotational analog, rotational equivalent of translational Newton's second law. So our torque is going to be the radius times the force, and it's perpendicular, so we don't have to worry about the angle. We know our rotational inertia from up here is 1/2 mr squared, so that's 1/2 mr squared. Alpha, one of these r's cancels, and we're left with alpha equals 2f over mr. And that was actually really simple. And there you go. In our last example, we have a frictionless pulley of science. It is given a rotational velocity this way, counterclockwise. I'm going to call counterclockwise positive, so that's the way it's going to begin with. But we have this mass attached to it here that's going to produce a torque this way, which will be negative, which will give us a negative angular or rotational acceleration. Now, they want us to sketch the position, velocity, acceleration graphs for when this mass goes up, stops, and then comes all the way back. So it's going to go up, slowing down, it's going to come back all the way back to where it started. So the key thing is we have an initial velocity and a negative acceleration. So let's see, here is theta versus time, here is omega versus time, and here is alpha versus time. So let's do the easiest one first, which will be, we know we have a negative acceleration. Now, we start with a omega that's positive, but we have a negative acceleration, so we're going to have a negative slope. But the thing is they want it to come all the way back to where we started. So we're going to have to stop somewhere at the top, and then we're going to have to end up going the same speed downward that we were going upward, because it's all symmetrical. So this would be negative omega naught down here. And then position would be, well, we start with a positive omega naught, we end with a negative omega naught, and we, at this time, I'm going to call that T1. T1, we should stop. So up here, we should have a slope of 0, omega equals 0. So that's going to be a downward facing parabola like this, and that should make sense because whenever we have a negative acceleration, we have a downward facing parabola. Okay, so I want you to notice that all of these problems that we've done are just like translational motion. It's just with a twist.